In this video, I'm going to talk about fundamentals of blockchain scaling. So parallel execution, gas limits, sharding, sidechains, and why it is crucial for regular users to be able to run full nodes, and therefore why the Solana approach to scaling, where that's not really possible, is unlikely to survive long term. First of all, I think it's useful to break these systems down into two main components, which I call the engine and the product. So the product in the case of Bitcoin would be the ledger, the coins, and the ability to send them and receive them, right? That is what Bitcoin exists to give as a product to the world. The engine then would be all of the components and mechanisms in cryptography that support the product. So proof of work and hashing and elliptic curves and the block times, all of these things, they're really just there to enable this ledger, this coin system, and they're really important, but the users generally don't really care about that stuff. The system exists to serve the product. And in the case of Ethereum and Solana, it's similar. The product, however, here is ledger plus programs or smart contracts. And what we have with layer ones is that this system, the ledger, the world state, which is the ledger plus programs, and all of these engine mechanisms, all of this stuff has to run on every computer in the network. So Bitcoin consists of a whole bunch of computers, and each of them stores the complete history and therefore the complete state of the ledger at any given time. And in the case of Solana and Ethereum, it's the same thing. Each computer in the system has a complete replica of the whole system. And as transactions are processed, each computer processes those transactions, sort of all of them in parallel. None of them are following any leader in the sense of like the leader has all the info and they have bits of it. No, each computer has complete copy of the whole system. And so therefore, if you add a whole bunch of computers to the system, if you add 10,000 more nodes to Bitcoin or Ethereum, or even 10,000 more miners or validators, right? In either case, you don't get any more speed. The system doesn't run any faster. You can't put more transactions through it because adding more compute to the network in this sense doesn't scale it. It doesn't do anything, right? It's still good to have more nodes, but it doesn't achieve scaling. So the question is, how do we scale these systems, right? How do you scale a blockchain? And we certainly need scaling because, at present, Bitcoin does something like 5 transactions per second at the L1. Ethereum does, 10, 15, depending on how you measure it. Visa does 1700, 2500. And I think blockchains collectively, to really do what they're destined to do, we need to reach in aggregate like 1 million plus transactions per second. So we definitely need to scale. So there's a whole landscape of scaling solutions. These can be broken down into layer 1 and layer 2 and beyond. And some of these I've talked about in previous videos. In this video, I'm going to talk just about layer 1 scaling, so this stuff here. Also side chains, which is sort of between these two. And in future videos, I'm going to go deeper into some of these layer 2 solutions. So first, side chains. Side chains are not really scaling solutions because we don't actually scale the main system. Like we don't actually make our chain, our system go faster. What we do instead is we just add more chains. We just have, 10 systems instead of 1. And the problem with doing that is that you're splitting up the economic security. So you might have your system, your Ethereum or whatever, with $100 billion worth of economic security, which is great. And then you go to some side chain and it has to have its own set of validators or miners or whatever, and they have to kind of bootstrap from scratch. So that system, the side chain, might have $10 million worth of economic security. So now you're losing that security of your main chain when you go to the side chain. So in order to actually achieve the 1 million TPS total with a sidechain approach, we would have to have thousands, tens of thousands of chains. So we would then be splitting our economic security into 10,000 pieces. So as an aggregate long-term kind of big vision scaling solution, sidechains really just don't work. There's the splitting of security, there's the problems with bridging, right? On a sidechain, you have no guarantees that things are going to execute according to some rules. Like the L1 doesn't have any real awareness of what's happening on the sidechain. Now, with L2s, which I'll talk about in the future, it's a little bit different. The L2 is actually constrained in terms of what it can do, and it offers certain like security guarantees right on the L1. The L1 actually constrains the L2. Here, in the case of sidechains, it's not like that. The sidechains are their own thing. You're at the mercy of their validator set and the total economic security and so on. And you have this splitting of the economic security. So generally, not really a good approach. Okay, now let's get into client efficiency, parallel execution, and raising the gas limit or increasing the block size. Basically, the Solana / Bitcoin Cash approach to scaling. Now, the first two cases are pretty simple. So for improved client efficiency, that's a totally reasonable way to scale. Client efficiency is always good. If you can make the client run faster in whatever way, that's generally a good thing. To be able to do more with the same amount of compute, that's generally just good. But that's a limited approach. You're not going to achieve 1000x the million transactions we need by just increasing client efficiency. They're already as efficient, not as they can get, but the devs are always trying to make efficient clients, not inefficient clients. And it's the same situation with parallel execution, right? Parallel execution is also great, but it's limited. So I saw this analysis on Twitter, which I couldn't find the tweet for, but they found that doing parallel execution in Ethereum, like in Geth, would achieve about a 40% speed up. And, 40% is good, but it's just not great. It's not 100x or 1000x. And, the reason for this is that parallel execution, like you're not splitting the execution, the running of the system across your 10,000 nodes and running in parallel in that sense. That would be sharding the system. That's different. This is where all of the nodes are still doing the same stuff. They're all running kind of in parallel, but not splitting the work. They're doing all the same work in kind of naively in parallel. And so when you apply parallel execution to that situation, all you're doing is these nodes, as they go through a block, they're all going through the same block, the same transactions, and applying it to the same state. But they just, as they go through the block, instead of going through the 100 transactions or whatever in order, 1, 2, 3, 4, they run them all, or they run some of them kind of in parallel on multiple CPU threads. And then one approach is they'll go back through and see which of those transactions actually depended on the ones before them. So if a transaction, if the first transaction made some swap in a Uniswap pool, and then the 10th transaction also made a swap in that pool, those two transactions depend on each other. The price will have changed a tiny bit for the second transaction. So if you just ran all of the transactions in the block in parallel at first, there's going to be an error there. So that's fine. You just run them all in parallel. Then go through and you'll see, okay, transaction 10, it actually depended on what transaction 1 did. So we have to re-execute, right? So you just go through and you re-execute the ones that have this dependency. And anyway, at the end of all of that process, you generally get something like a 40% speed up. So it's just parallel execution is not going to solve scaling in any significant way. It's just a nice to have, really. Okay, now let's talk about increasing the block size or gas limit, basically the Solana approach. And right now, as it stands, Ethereum could easily 10x its gas limit and basically have 10 times the transaction volume going through it. There's no real reason we couldn't do that in principle. The result of doing that, though, would be that we're cramming 10x the transaction volume through the system, which means that each underlying node has to also do 10x the computation, 10x the work. And the problem with doing that is that if we're requiring all of these nodes to do that much more work, we're going to potentially lose the lower end machines in this network, right? They're not going to be able to keep up with this new high demand. And taken, further, if we extend or increase the gas limit far enough, then you get into the situation, which is basically where Solana is, where to run a node, the only machines that can really keep up with the system, they have to be run in data centers on high-end machines with really fast internet. Or maybe you can run it in a residential situation, but you're spending, 15 grand on your machine and you need like a super reliable, super fast internet. And the result of that is just that you have this much smaller set of nodes running the network. And I'll talk about in a minute why that is actually a big problem, right? Because you might think, who cares? I don't really care if I run a node as long as the system works and these guys can have their high-end machines and we have a fast system. Like, what's the problem? But it's crucial that there's a culture of users running their own nodes and verifying the chain themselves, not pinging out to some server, some third party to get the state of the chain and so on. It's crucial that the users are running their own nodes, and I'll explain that in a minute. But anyway, right now, Ethereum could, in principle, raise its gas limit. And okay, so we know that if we did that to a large degree, the weaker nodes in the network would fall off, right? And Ethereum has this target of, we want a $2,500 laptop, like a mid-range consumer laptop, to be enough to stay synced to the network, because we want users to be able to run nodes for reasons I'll explain later. And so that makes sense. But okay, so even if you look at the current situation, like this little chart here is, the data in this chart is essentially taken from a node that I actually run. And I'm showing here this progression of time where each of these black lines represents the time in which a new block is created, the slot, the slot time. And so every 12 seconds, we have the creation of a new block. So what happens next is that block has to propagate through the network, right? That's these orange bars here. This part I had to estimate. I don't know the average propagation time, but there's some propagation time for the blocks to move through the network. Then you have some block processing time. Now, this is the interesting part. The block processing time on my reference machine, which, by the way, is not a high-end machine. I spent about $1,500 on it like 3 years ago. It's a Linux system. It's just a pretty basic system with a good SSD, I guess. But it processes blocks pretty quickly. So the 7-day chart here gives an idea of the processing time. It's about 300 to 500, maybe 600 milliseconds per block. And so if we take that and, put it to scale with the 12-second overall time between blocks, we can see that the time that my machine takes to process a given block is actually pretty small relative to the overall sort of window that it has to process the block. It seems like it has a lot of room, right? If this propagation time is correct, then my node gets the block after like a second or two, and then it processes it in like 500 milliseconds or 400 milliseconds. And then we have this huge gap. So it looks like we could, why not do a 5x? Or maybe even a 10x? It seems like you could fit a block that takes, a lot longer to process into this gap, right? But there's reasons for not doing that that are not obvious upon first glance. So the first, obviously, is that, as I mentioned, there's the propagation time. So even if your blocks are pretty quick to process, if you're in some, remote area in the network, you might not even get the blocks on average until like 5 seconds, 6 seconds into that slot. So you might only have really like a couple seconds to process that block, or else you're going to start falling behind, right? So that's one thing. The other thing is that there's the question of syncing, right? So if each block took like close to the maximum 12 seconds to process, including the propagation time, you would still have this problem of, okay, if you're syncing from scratch, right, as a new node, you need to be able to process a block like a lot faster than they're coming in, because you need to catch up to this chain tip, the head, which is advancing. You need to be moving faster than the head is advancing, or you never catch the head, right? So that's another factor. And another one is that we have to consider the state growth and the growth of the chain, right? And these are different things. Of course, the state is the total set of all of the accounts and contracts and their storage at any given time. So that's like the size of this Ethereum world. And then the chain, of course, is the history, right? So these are two different things that we have to keep an eye on their growth in different ways, right? As the state gets bigger, it becomes harder to process a transaction, actually, because when the state becomes very large, a node who's going to process a transaction for some account, it has to essentially search through this huge state, this huge data object on its disk. It has to look through and find the relevant account, right? So state growth is becoming, it's actually more of a bottleneck in most ways than the actual CPU processing time of a block. So a block might only take my machine 300 or 400 milliseconds to process, but it might be growing the state, the total size of that object that my disk has to store. And right now, there's no state expiry presently. So this object just keeps getting bigger on my machine. And so if we were to 10x the gas limit without doing anything else, we're also 10xing the rate of growth of that giant state object, which is, it starts to slow down the accesses, and it just becomes, it also just requires that node operators like myself have to upgrade their storage, their SSD. So we want to keep an eye and sort of limit the demands on the multiple different resources in the given computer, right? We have compute, we have storage, and we have bandwidth. And so if we want regular users to be able to run a $2,500 machine and stay synced, we need to keep the compute used at like 5 to 10%, maybe 10, 15% even, so that they can, again, like rip through those blocks when they're catching up, when they're syncing, and so their CPU isn't being totally like maxed out, right? So that you need headroom for the operating system and so on. And then also the storage. We would like the storage to be like reasonable, right? The target kind of originally was like 0.5 terabyte, which is, I think, pretty small now. My machine has like a 2 or maybe, I think, a 2 terabyte disk. But it basically should just be an affordable consumer level, not a super high end disk, SSD. And then bandwidth, right? Again, we have to consider these network conditions, both in terms of the time it takes for a block to arrive at a given machine, and then also the amount of data in the block, right? Because if you're maxing out someone's network connection, then it's going to be a problem, right? Like if you're running a node, but your node is using your entire network for your residence, for your home, then you're not going to run the node. You want to be able to watch Netflix and whatnot, right? So this is the approach that Solana is taking, right? It's taking this approach of crank up those variables, crank up the gas limit, the equivalent of the gas limit, and we're going to just be okay with the fact that the nodes are going to be run in these, mostly in data centers, high-end machines, super fast network conditions, etc. And the result of all of that is the advertised and, the actual high throughput of Solana, 2,700 transactions per second or whatever. Some percentage of those are actually votes, which I would say shouldn't really be counted. If Ethereum counted their attestations, you could say Ethereum is running at like 4,700 transactions per second, which is obviously not like what people really mean when they say transactions per second. So that being considered, Solana is more at like 1,600, which are also heavily subsidized, by the way. But anyway, the result of all of that is a fast system, but it's more centralized in the sense that fewer nodes, higher end nodes, fewer nodes, and fewer people are running the system. And there's some fragility in that for obvious reasons, right? The more obvious reasons for that fragility is that fewer machines means less have to be destroyed for the whole system to vanish, obviously. These machines being run in data centers means that it's professionals mostly who are doing it. So they're perhaps part of an organization, a company that can be seized by some government and required to shut down. Uh, they're there's just it's just less resilient, right? It's less like World War III proof or apocalypse proof if they're all in these data centers. But the more subtle and interesting consideration here is the importance of users running nodes for this entirely different attack vector that I don't think many people know of. Okay, so suppose we have this situation where a small number of very powerful machines are running our system like this. This is the situation with Solana. We could imagine this being the situation with Ethereum too if we cranked up the gas limit to 10x, 20x, something like that. All of the rest of the computers, the users in this network, these guys have to get their information about the state of the chain from those nodes, right? Because they really can't run the nodes themselves. Okay, so what can happen here is we have the situation where it's a small number of powerful machines. It's not easy to run a node. So you have a small number of people, right, who ultimately control this hardware. Now, these people are perhaps in some shared communications, in forums, in private group chats. And this is especially true as that number gets smaller, right? If you're talking about a handful of operators who run a big mining operation or run the big mining operations for the chain, it might literally be like 6 people who ultimately are controlling half of the hash power, right? And yes, I know mining pools, people can leave the mining pools if something bad happens, but keep listening to how this works. So if these people are a small group and they know each other or they have some communications, what they could do is this. They say, okay, guys, listen, we are underfunded or whatever, blah, blah, blah. We deserve some more money for our efforts because we're running the system and we're the people really keeping it running. So they say, we're going to create let's call it a sustainable infrastructure fund. And what we'll do is when America is asleep, when our bulk of our people are asleep, we're going to introduce into the system a fund, a multi-sig, let's say, that is created, which is seeded with 10,000 ETH out of thin air. And the way that they would actually do this is not hard. All you would have to do, if we're talking about Ethereum, you would introduce a patch into a client or multiple clients, for example, a patch into Geth, which would simply have like an if statement. If block is greater than our target, introduce this change. Like this is how hard forks work. Like you're creating a change at the protocol level. So they could do that. They could introduce a little change into the client, which is saying at this block, accept this transaction or this change, whatever, that creates this contract with 10,000, this multi-sig contract with 10,000 ETH, right? Now, if they do that and they kind of coordinate on that, no one's going to notice. Like the system just keeps going. If this happens, say at night or whatever, and you have this situation where people are not running their own nodes, then they don't even know that this has happened. You don't get like an alert, right? No one would realize this has happened until it gets out somehow, or someone like downloads a bunch of blocks for some reason. Someone would have to check somehow. Like they don't have their own copy. So what happens is this multi-sig is created with 10,000 ETH or whatever, a million SOL or something. And by the time the people notice, because the people are going to be furious, right? By the time they notice, 6 hours or 8 hours or 10 hours of stuff has happened after that block. That block that we, should have deemed invalid, we didn't see it. So now there's like a day's worth of financial activity and all the stuff that happens on these chains on top of that block. So now the community's in this really tricky situation. Like, okay, these guys created this fund. They're branding it as like this sustainable whatever. And meanwhile, they're on Twitter being like, guys, this is really like, it's going to help make the system stronger. So there's all this confusion. And then it's like, do we roll back? If we roll back, we're going to delete all this history from the day. And each hour that passes that you don't roll back becomes harder to roll back, right? So if they created this fund with like a tactfully or tactically, decided upon amount of funding, like if it's not too much, like maybe 100 ETH or 1,000 ETH or something, then it's not even worth it. Then you're just like, well, rolling back would cost us more money and all this chaos, so we're just going to go with it, right? So that's how this could happen. And so the small subset of these entities who are running the infrastructure, running the nodes, they can kind of rug the whole collective community, right? And there's not a lot you can do about it. Now, if the users and the wider community are running nodes themselves, this doesn't work, right? Because what they're going to do is, if they try to do this attack, they patch their clients so that they're going to accept this block, this transaction that creates this fund. But when that block is proposed, all of the rest of the nodes are going to see it as invalid because they don't have this patch. They didn't change their client software to accept this kind of nefarious transaction. So they're going to see this transaction and be like, that's invalid. That's not a valid transaction. So this block is not valid. So we throw the whole thing out and we're just going to wait, right? That slot, invalid block was proposed. So we throw it away and wait for the next slot. And hopefully we get a valid block then. Now, if these validators are trying to continue building on that false history or that nefarious fork, it's just not gonna, the community is gonna see, okay, they're trying to build on a block which was not valid. So therefore this new block is not valid, and so on and on. Like, you can't build on top of a valid block. The software that the users are running are going to reject all of them. So they would just see a bunch of empty blocks and the chain would appear to have stopped, right? And if there's some, operators who aren't in on this, then the blocks that they propose would be seen as, they would be valid blocks. So the chain might not actually halt entirely, but it would be hugely degraded service. And, the community is going to be like, wow, the system basically has 50% empty blocks. What is going on? And they're going to get found out. They'll be able to see that this transaction was created. And the whole thing doesn't work, right? So that's why the proof of work or proof of stake, that sort of economic incentive system for, aligning the system onto a fork, onto a certain history, that actually doesn't cover, that alone doesn't protect you from this sort of protocol level attack, right? This is why you actually need, it's not sufficient to have a bunch of nodes in servers, in these high-end machines with, say, whatever, $200 billion worth of economic security. That's great. That protects you in a certain sense, but it does not protect you against this kind of protocol level, injection of nefarious things, right? For that, you need a culture. You need people to be running nodes, right? And of course, in the case of Ethereum, most users are not running nodes, right? We have Infura and these things that we basically just grab information from. But it's certainly possible. I have a node down there and it's a basic machine. It wasn't hard to set up. And also there's, on the Ethereum roadmap, a plan for reducing the requirements, the hardware requirements of validating the state yourself on your own machines, such that eventually we arrive at a future where the whole of Ethereum is validated via snarks, ZK proofs, which can be done very quickly. And so ultimately the entire state and the changes to the state will be verifiable on something as low power as a smartphone, which that is huge, right? Then it's just, you just download an app and every app is actually just verifying the chain, and that's your interaction with the system. So this kind of attack just becomes impossible, right? So that's kind of that's one of the hidden risks, the hidden costs that you pay for this sort of the Solana approach to scaling, where you have these high-end machines running the whole system. By the way, if you want to learn more about this kind of approach, or this attack, I should say, check out this post by Vitalik. He explains it quite well. And also this post by Dankrad. It really gets into the nuances between, the economic security of the consensus model and then the protocol level sort of aspect of security. So the next thing is sharding. And this is, pretty simple in a sense. Basically, I'm sure you're familiar with how this works. We're essentially breaking the system into many pieces. So with Ethereum, we would have, for example, like 64 Ethereums, basically. But they would all have the same, they would share security, right? We would have this system for sort of shuffling the validators across all of those different shards in such a way that each of them was just as secure as if all of those validators were securing just that one shard, right? And this is a viable approach. This was the original scaling approach that Ethereum was going to take, but it's complex. It's hard to actually execute. It introduces a lot of complexity. And for Ethereum, I think the target was 64 shards, which is, substantial, 64x. But it's really not, I don't think it's enough, right? We have to get more than 64x. Ideally, we can get into the thousands and hit that million TPS that we really want, ultimately. And so this approach was abandoned in favor of rollups, because rollups are just superior. Like, you get kind of the same result, except better in like every way. You have this there's maybe sort of nuances and trade-offs, but in most ways, it's just better. You can have more than 64 little Ethereums. You can have many, tons of them. And it's much more of like a free market approach. Each L2, in the case of rollups, can take all these kinds of different trade-offs and different approaches, and like each of them can become their own little realm, their own ecosystem, their own business. And it's just this free, open, competitive approach, right? And it's just way simpler and just better. So that's the approach being taken now, and I will talk about that in a future video. Okay, thanks for watching. The next video will probably be on Bitcoin Lightning, because I want to get into state channels and talking about that approach to scaling. Then I'm going to get into layer 2s and give kind of a high-level overview of the advantages of layer 2s and this whole roll-ups approach to scaling. So it should be a series where we kind of cover all of the major scaling approaches. And then I also have a video that's pretty much ready to shoot on EigenLayer. So that one should be really interesting, because EigenLayer I think is super interesting, and it is kind of an extension of sorts of this whole scaling thing. It's a way to scale the economic security of a system to like everything, to more stuff. So anyway, I'll talk about that in that video, and thanks for watching, and see you next time. Bye.